Okay, so let's continue with our numerical Fourier analysis. So let's think we have talk about grid functions at first. That is functions restricted to a grid, say to a discrete domain. Okay, so so as I wrote last time, let me remember how to do a little quick review. So this factor here sometimes is used, sometimes it only uses in the inverse. So that's just paying attention which one we're using. Okay, so this is what we did last time. We had this formula, and we have this formula. Whoops. All right, here it's clear. This fact that we have only this. So I forgot to say this last time, and I'll come back to this maybe not today. You'll see. I'm going to connect these things. Maybe not today, maybe next week. We'll see. But anyway, we say that then. So this is a thing I didn't mention. Excuse me. Last time we talked about this. So this is the Fourier coefficient, right? So this is basically a discrete, to some extent, Fourier transform. We have this delta x here, which when we do a Fourier series, it doesn't appear. This delta x here is because we're doing a trapezoidal rule of the Fourier transform, right, on the whole line. Okay, so that very simple things, but to set our minds. Sometimes when, long ago, decades ago, studying a student studying first, we always get, oh, wait a minute, am I in a periodic setting or on the whole line periodic setting? You have a Fourier series because on an interval, only a certain countable number of frequencies fit there. Right? On the whole line, no, you don't have that restriction. So when we're not doing anything numerical, we have, when solving, say, differential equations, we think either of a Fourier series or a Fourier transform, right? Which is basically, in terms of applications, it's a superposition of modes, a discrete one, which is Fourier series, right? Infinitely many, but discrete, or a continuum, which is Fourier transform. We're summing, we're superimposing. The integral is a superposition, just like the sum, and we have all modes. Here, when we have a function, we're on the whole line, okay? So maybe let me make sure, right? This continues like that, just for clarity. And and I have a grid function. I have a function, and I restrict it to this domain, which is discrete, I immediately eliminate some frequencies, right? Wave numbers, spatial frequencies, as I mentioned last time, right? Which means right, we cannot see frequencies, wave numbers, which are spatial frequencies, higher than these guys. So we have a band limited function. So this is what it means, band limited. It's a band of frequencies. And I'm going to follow at some points the book by Trefethen, which is a very good book, Spectral Methods in MATLAB. And we're going to see, I think next week, not today, some theorems which are very useful for numerics. Starts with the Pali-Wiener theorem, which comes from harmonic analysis, which then we'll see its discrete version, okay? And we'll see properties of band-limited functions, okay? So this is the band of frequencies that can live on the grid. And then I'll mention today, not today, but I'll mention soon also the Poisson summation formula and aliasing that I mentioned last time. Okay, so those are the things I wanted to sort of remind ourselves from last class, sorry. So this is the discrete Fourier transform, so let me put it here, which the FFT is a fast way of computing these guys. And this is how does this guy looks when we have this band-limited function, right, VQ, and we come back, we can only integrate over this band here, okay? So just preparing, one thing that I think I'll talk today is, who has heard here of a sinc function? S-I-N-C, not sinking, or a sinc function. Well, a sinc function, okay, a sinc function which is something actually to some extent simple. I mean, simple. It's just sine of x over x, or sine of px over px, whatever, depending on how you scale things. It's a very interesting function, useful function, in things that we're going to see starting today. And in the book of Trefethen, he explores this very much. So this is basically the sinc function. And a sinc function, which I'll be drawing it today, later in the class, is a band-limited function. You will see this, okay? Or if we switch things around, and that's, I almost forgot this remark, is that, look, a band-limited function which has a constant spectrum, okay, over this interval, we can actually think it reverse. If we have a square function, just like our pollution wave in that problem we saw long ago, the Fourier transform of this square wave is a sinc function. So just see sinc function appears when we talk about spectral method. It's a very useful function. Right now, just don't worry about it. Just think, oh, there's a new name of a function that will be useful, okay? Which is band limited. Okay. Things also that we need to mention. Okay, so some, in the notes I'm calling this important facts. About, let me put it like this, discrete Fourier analysis is that, well, if we're not talking about Fourier, right, we have Parseval's equality, right? Where this is the L2 norm, right? And this is Parseval. So basically, the L2 norm of the function is equal to the L2 norm in Fourier space. Okay, and this is very useful. And this is basically one of the important things for going into von Neumann analysis, which stability analysis, which we will see soon, but maybe next week, okay? Maybe not next week, because I want to first give you another problem. We'll see how they order. So do we have, so von Neumann, as you will see, is based on the fact that we have also discrete Parseval's equality, which is this. So let me write it and then explain the notation, or else if I talk and write at the same time, I might get things wrong. So we can call this Parseval. I don't know if this is exactly, I haven't checked in the book, but as maybe called Parseval on the grid. Okay, so discrete Parseval. Okay, so let me explain the notation. This is just the usual Parseval. Okay, so the L2 norm in the physical space is the same as the L2 norm in Fourier space. Okay, now. So this is squared, right? So now what this means, so think of this, okay? Think of this. Now we're doing the L2 norm of Fourier coefficients. But why is this delta x appearing here? Maybe let me start from the other side. Last class, I mentioned about this notation here. Okay, so we're going to check this equality. Okay, this equality means the discrete Parseval, which is Parseval in Fourier space is equal to Parseval in physical space. It's just reversed, okay? Now, I have to just explain the notation, and then we're going to check this. So the notation here is, remember that Parseval, discrete Parseval, or discrete L2 norm in physical space is done as an integral, right? So like a trapezoidal rule integral on the whole line. So here it is, right? So this notation, because Vj is sort of a vector, right? It's right points on the grid. So this notation is just to say it's like to write it as a continuum norm, right? An L2 norm, a big L2 norm as an integration, as a numerical integration, because actually if I did only this, it would be the notation of linear algebra, little L2 norm. That's all. So the notation is just to connect with the continuum one, and this puts the grid spacing. Okay, that's all. So it's like little L2 times delta x. Nothing more than that, okay? And then here, right, at one point actually I was reading my notes again. I said, wait a minute, why did I put delta x here, right? Delta x here, because here I'm integrating in k, in wave number, in Fourier space, okay? But this delta x here is just to remind us that we actually have a grid function because it's here. It depends on this parameter. So think of this as a parameter where it tells us, say, there's many ways of saying a filter, or maybe I came up with a better word right now, which is better in English, which is a cutoff, where you cut things because you can't see frequencies beyond this one, right? Remember that on the grid, right? If I have something too fast, I gave you the example of aliasing for the sawtooth mode, right? We're going to talk about the sawtooth mode soon in a problem that I don't know if I'll start today or next week, which is a problem I use in the PDEs course, I use in the fluids course, which is an interface problem, which has legitimate dynamical instability. It deals with singular integrals, blah, blah, blah. So how can we integrate the singular integral? We're going to see all that. Okay? So remember that I said the sawtooth mode is that one that's plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. If my grid is not fast enough, I would just see plus 1, plus 1, plus 1, plus 1. So that's an aliasing. Okay? So that's like a filter to some extent, like, which is not quite a filter. It's aliasing. It gets reassigned to another position. Right? It goes to a constant. So we can think of this as also as a cutoff. The words are not so important. Just I'm saying different words so that you can, in your head, have different sort of intuitions for what's going on. Okay, so this delta x here, even though we're integrating in Fourier space, is just to tell us up to where we're going. It's like a parameter for which frequencies, or which is the most appropriate way of saying is we're doing a band-limited integration. Okay, that's the most sort of sharp definition, but the other ones are good because it's like it generates an intuition for frequencies being used and so on. Okay, so now what we have to check, I'll do it, no, it's in the notes, I'll do it for you quickly, is we have to check that this is okay, which then confirms that we have a discrete Parseval. Okay? And the discrete Parseval is useful because it's basically going to give us the way of going. That's, I think, what was the way that led von Neumann to do the von Neumann stability analysis. Because remember, I'm going to remind you, those sort of estimates we were doing was L2 estimate of the solution controlled by a constant CT and the L2 norm of the initial condition and so on. We can do that in Fourier too. And for numerical methods, it will be easier. Okay? All right. So these are some facts. So basically what we're seeing, look, just so we well, I write different. So basically we have Parseval defined. Okay, just like that, just indicate a grid, just sort of notation. Okay, so now let's check what we did, which is also good to know that we're okay with the notation. So this is just the definition. Let's write the definition again. Okay. Now, I'm not going to do the whole thing because it's in the notes, and it's relatively straightforward. But just, let me just indicate how this goes. Okay, so what did I do here? Right, I just did that from the definition. We had this, okay, but this guy here, right, which is here, this guy here, sorry, I forgot the 2 here. This guy here, I can write it, since this can be complex, right? I can write its conjugate times itself. But then itself, I use the definition. Okay? And then admitting that we can sort of switch these guys, okay, so we have regularity, so we can play with these guys and switch this around, I can write, I'm going to skip one line, it's in the notes, you check. let me call attention here because I was with the conjugate on top of all this guy. Okay. And this will give us this. Okay? So I'm just skipping one step. You can do it. So basically, if we have enough, right, regularity, we can switch the summation and so on, which has to do with the case of this guy. This guy, we can write this like this, right? Let's see, I had the, do I have the conjugates right? I think so, right? The minus disappearing. Wait, you check the details, but this is the main idea, and we get the discrete Parseval. Then, this allows us, well, to seek results such as this. Okay, and this is a little bit, right, in a loose way, this a little bit will be the spirit of what we'll see in von Neumann analysis, which basically now instead of sort of controlling the L2 norm, I think I forgot the 2 here, no, it's right with square root. Instead of the norm, L2 norm of our function, we control the L2 norm through discrete Parseval of the Fourier transform through that of the, say, initial conditions, depending on if it's a multi-step or not, right? That's basically the idea a little bit behind von Neumann. We're going to go through Fourier, controlling things in Fourier space, thinking of discrete Parseval. Okay, so let me tell our roadmap for the moment. So before going to von Neumann analysis, which will seek things like this, I want to exercise some things with you on Fourier, right? Fourier analysis of numerical methods, also stability problem with, I told you, with something weird at first, right? Some of you already saw, and I will refresh to those of you here who haven't seen a singular integral. And a singular integral is something very nice from the modeling and challenging from the modeling point of view. So in the fluids course and in the PD's course, I explain in more detail where this modeling comes from. Here I'm going to a little bit just give us the differential equations, explain a little bit, right? But as you will see, we can actually deal with a singular integral, so an integral that does not make sense in the Riemann sense numerically. And there's a result that I find it spectacular, which is there's an alternate trapezoidal rule which skips every other point, which gives us the result of a singular integral with spectral accuracy. What is spectral accuracy? I suppose you don't know, right? And it's not that common to be used, but you'll see what that definition of spectral accuracy in opposition to algebraic accuracy. Algebraic accuracy is, for example, center differency. It's order delta x squared. And it will be order delta x squared independent of the regularity of your function. If your function has 3 or 10,000 derivatives, it's order delta x squared. When you have spectral accuracy, and with Fourier in general you have, the accuracy depends on the regularity of the function. So we will see that we can, for example, with Fourier, it's very simple. I don't know if you ever thought of this, but it's very simple. You can, for example, differentiate cosine of 4x with spectral accuracy, which means that you only have round-off error. You do not have truncation error. from your faces, I can see this is new to you, maybe. Is it new to you? Do you know what I'm talking about? Right? Some of you know. So this is very nice. So you can calculate something which will, when you use spectral method or use Fourier, which is of high precision, and the precision gets better if the function is smoother. That's sort of along the lines of the Pauli-Wiener theorem that I'll present to us maybe next week, early next week, that tells us exactly how do things get better with the regularity of the function. So it's a theorem from harmonic analysis, but that has its, in Trefethen's book, it has its numerical counterpart, and which is very good, and probably will give you, exercises to see that in practice. Okay, so let's go in. That's the direction where we're going right now before we do the von Neumann analysis. So we get intuition with all these things. Okay, so right. So what I'm going to do now is I'm going to do it fast and simple. So basically, I'm going to be following Trefethen. It's a very good book. I like it very much. Trefethen. It's a signed book. There's other books. There's some classical books in spectral methods, right? I'll mention to you when it comes the time. Maybe we can do some reading there as an exercise. We'll see. Okay? So let's see properties of, let me put it like this, Fourier properties. Okay, so some of them are easy to check. And let me use now, I think the notation from the Fourier from Trefethen is slightly different from what I was using, but it's good to call attention. So take a function in L2. This is called, this will be my notation when necessary for the Fourier transform. Okay. So in Trefethen's book, like this. And the inverse okay. So here it's wrong. Right? Okay, there's a typo in the notes. Oops, sorry. Okay, where we have x on the real line. And in this case, okay, so those are the things to pay attention. So you know what without me explaining much, you probably know what I'm talking about, right? This constant in front of the Fourier transform depends on the book, the author. Sometimes it appears like this. I usually tend to prefer like that so I don't forget Werner's growth, so I have the same constant on both ways, or it's just a rescaling, or in Trefethen's book, he uses only in the inverse. Okay, and then you pay attention. That does a rescaling for Parseval. That's all, right? So sometimes we got to pay attention because we might calculate things and miss by a certain value, okay? Okay, no big deal, right? Just calling it, that's why I wanted to write this, just to call attention, right? And so here we have, right, our Fourier. So I work with waves, So I always like to think, right, very simple. My wave is a superposition of Fourier modes with this amplitude. One way of thinking. Or if you like signals, if you're doing computer graphics, whatever you do it, or if you just write, or if you just purely a mathematical representation, is that this is a basis. These are the coefficients for representing the function, right? Using trigonometric representation. No big deal. I always like to think about waves, but you're not obliged to think about waves. Okay? So Trefethen does a few things which is good for us to be alert, and also so that the sinc function will come in, right? Which we'll see in his book, not now, but things, maybe I'll give you certainly at one point exercises, computation exercise from the book and other things. So look at this. When we do some averaging to some extent of a function, right? If the function has a discontinuity or something like that, some sort of kink, right, a corner, and we do some sort of averaging of it. I'm not explaining exactly what I mean by averaging. Averaging tends to smooth things out, okay? So one exercise that Trefethen does is this. So he writes a convolution, okay? And if you do things in MATLAB, there's many commands that sort of facilitates our use of these things. I mean, for numerical convolution and so on. Okay, so here's a convolution. So it doesn't matter if you do it with U sliding or V sliding, right? Right, it's the same. And we know a famous thing of convolution, which is great in Fourier space, right? That becomes a product. So the Fourier transform of U star V is equal to U which is the product, okay? So, excuse me. So Trefethen does then the following example, which is good for us to set our intuition in our communication, and also so I can present you in one of the many ways, present you the sinc function, right? That not all of you have heard about it. Okay, so look at this. Let's have this example. Let me write this here. Where U, let me actually do the figure, right? U is this square wave like this. 1 minus 1 1/2. Okay, so this square wave, or rectangular wave, better said, right? But even though sometimes we just say square wave. Okay, if it's propagating, but this is stationary. And then some interesting facts, okay? So let me write this maybe here. I wanted to keep this black part, so that's why I'm doing this. So some facts. One over square root of 2, and, oh, let me put it down here. And if we do the Fourier transform, of this guy, right? It's simple. We can do this. This is equal whoops, to sine of k over k, which is what we call sinc of k, and which is sometimes, this is good, I didn't know this until sometime, which is, this was also known as the Whittaker cardinal functions. When was this? 1915, right? The sinc function. Okay, and in Trefethen's notation, sometimes he writes it like this. Okay, this S of H is this function. So this function is interesting because of the following. Look, let me do a picture here. If we do the Fourier transform of this guy, my drawing, of course, is not going to be very good. In Trefethen's book, there's a picture more or less like this. Okay. And which we see this, okay? So this basically is a function, which is this sine that decays, right, with as x. And what is interesting, okay, I'm not going to mention here, but what is interesting too, as we'll see later, but let me mention that to you, is that look at this, or maybe not here. So let me reverse things. Look at this. This function here look at this function here, the S of H, right? It has a very nice property. And let me give you a hint. It looks like it's a continuous guy that act as if I make it as a grid function, look, this is a function, right? It has a scaling by H. But if I make this guy a grid function, it becomes what? 0, it's 1. At H, which is here, H, it's 0. 2H, 2 pi, it's 0. So it's like the Kronecker delta. Of course, you can shift this guy. So in the book by Trefethen, when you see spectral methods, sometimes you use this guy, shifted, x minus blah, 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 and you have basically a Kronecker delta type guy. But in between the grid, right, it's sort of more or less oscillating as this. I don't want to draw it. You see in the book, there's good drawings. So this guy is an interesting guy to use to manipulate things, as you will see later on. And it is a delta Kronecker. Now, if I do the Fourier transform, we're going to see soon, very quickly, and I'm not going to write all of them. It's here in the notes, properties of Fourier transform, okay? So if you Fourier transform using the inverse or whatever, if you change the rows, but here you can understand is that if I Fourier transform this guy, what is the spectrum of this guy in Fourier space? Modulo a sine, whatever that might happen. It's a little bit like reversing this, right? You will see, look, the Fourier transform has this difference only of signs here to some extent, right? Modulo, forget about the constant, right? So maybe I won't write all the properties, or else I'm going to spend too much time of the class, but it's here in the notes, it's in the book. There's like 1 million of properties for Fourier transform. If you Fourier transform and you conjugate, if you do this, if you do that, I'll mention just a few because I think they're interesting. But one is, if you apply the inversion formula for this guy, is like putting a minus, there's a conjugation or a minus sign. So you can see at least that the shape of the Fourier transform of this guy is this, which means something very interesting. The sink in physical space is like a Kronecker delta, right? You're okay with that, right? It's 1 on a given point and 0 on the others. And then I can just shift this guy by a grid point, and it'll be the Kronecker delta of that other node. So you can see a little bit of how you can use this, a little bit of a basis for writing things in a continuous form to represent something discrete in a useful way, blah, 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 okay? Now, the other interesting thing is that this guy, which is a Kronecker delta type guy, is a band-limited function if we reverse the rows. It only, right? So it's a very good representation for grid functions. And of course, if I let delta H go to 0, this guy will become wider and wider. And sort of in the limit, it would look, so it would be a little bit like a truncation of a Dirac delta function. The Dirac function has all frequencies the same and going all the way to infinity, okay? So things for us to have in the back of our minds. Okay, now let's go back to the convolution. So what Trefethen presents, let's see if I don't lose track here, is that he then does this, and then he does this graph. So this is U, this is U hat, and this is U star U. And if you do the Fourier transform of this, right? So you already see that if you do the guy convolved with itself, it has a discontinuity in the first derivative, but the function already does not have a discontinuity. Okay, it's already a smoothing effect. Okay, and this will then give us here a sinc squared of k, which is a guy that looks like this, but just a little thinner, okay? I'm not going to do the drawings properly. And then Trefethen shows also that if you do U convolved with U, and you convolve it again with U, right? This looks like more like a smooth function, more or less going from -3 to 3 and so on. And of course, in Fourier, I don't need to write this, it's going to be sinc cubed. Yes? The sinc squared does not have any negative part. Yeah, so my drawing is terrible. Yes. Thank you. Oops. So you don't complain, okay? Thank you. Right? It doesn't have any negative part. Of course. But it has these oscillations and so on, right? Thank you. Right? And there you go. Okay. So these are facts, right? From Fourier analysis. Let me go to the other, because I'm going to list things. Let me go to this side of the board. And let's see now, I'm going to list, not all, okay? Because in the book, in the notes, there's a big list of Fourier properties, right? Some Of course, most of them quite obvious, not difficult to check. But I'm going to list to you some properties, some Fourier transform properties that gives us also, it's of numerical use, okay? That's basically what I want to do, okay. So, let me put it this way, useful properties. So one is like this. Let me put the hat big, right? This property is of numerical use, right? And we use it a lot. And you're going to use it. If you want to differentiate a function, and this is a differentiation with spectral accuracy. In particular, if you have so you need to have for numerical to use FFT. So we can do this using FFT, right? We either have periodic boundary conditions, or we have a function like the Gaussian, as an example, that decays exponentially. And if you put the ends of your computational domain far away, the Gaussian is not compact support, right? Because compact support is compact support, right? It's zero. But it's almost effectively zero. So therefore, you can actually do the derivative of a Gaussian using FFT with very high accuracy, just doing this. You do the FFT of the function, right? You multiply it by IK, you do the inverse FFT, and you have the derivative of the function, right? So this is sometimes called the symbol of the operator, which is when you multiply, I'll come back to this many times, but the symbol of the operator, which for differentiation, it's basically the symbol of a differentiation if you have like many derivatives, right? So if you have an operator like this, look. Right? In Fourier space, this is a polynomial in K. Do you agree? Right? Because here I'm going to get a K squared. I'm going to get a K, of course, with the powers of I. And here I'm not going to get anything. Right? So then the polynomial in K would be the symbol here for me to just differentiate these goals. I go to Fourier, I multiply by the symbol, which is a polynomial in K, come back. I've already done all these guys at once, if needed. Okay? So very, very simple. Okay, so this is already one property. So we have many other properties, facts. So let me write just a few of them, just to be complete. So what is this? This is, of course, linearity, right? Now, there's one that's nice, which is translation. Translation is this. So I can write okay? So this property is translation. This is linearity. So look at this. This property is of numerical interest. Can you see the numerical interest of this? Let me draw a picture to sort of induce you to that. And now let me write this in a slightly different notation. You see, it's like a Fourier interpolation, right? Because the interesting thing is this is like we can think of this as like a rotation, right, of things, because just right, if you want to call it this way, doesn't really matter. But this is like an interpolation, which means I have this is the FFT, this is the Fourier spectrum of the function u of x, where I've used the nodes, right? So if I go to Fourier space and multiply by I, k, epsilon, all the Fourier amplitudes, and come back, I am getting all function values at all these points here. So let me put it like this. Right? So it's like a Fourier interpolation, and it has, say, spectral accuracy. I'll have to define spectral accuracy soon. But as an example, if I'm doing that for cosine of 4x, it's exact up to round of error, getting these midpoint values, okay? Of course, we don't need to do that for cosine 4x. It's just like, right, it's just to test things. Another case, modulation. And this is also good, has an interpretation with waves, right? So modulation is if I do this, this is equal to, so it's here's a shift in physical space, here's a shift in Fourier space. And modulation, for example, here's an example, which in fluids, in waves, it's common to use or to analyze. So in waves, this is usually sort of a monochromatic carrier. Why monochromatic carrier? Because it's this guy here. The carrier, monochromatic carrier, it has only one frequency. And this is the envelope. So for example, this could be sort of a Gaussian in that case, okay? So it does this modulation. So what this does in Fourier space, it gets the spectrum of the Gaussian and shifts by the frequency of the carrier wave. Okay? In water waves, which is my area of most of expertise, this is called a wave train, right? So this from the surfer's jargon is a series of waves, right? So here comes this wave, then comes this wave, then comes this wave, then right? And so this is a modulated wave train, and usually people, when they're surfing on the beach, the expert surfers, when there's nothing happening, then you see a series of waves coming. Usually the good guys don't catch the first wave, because there's usually a slightly bigger one coming afterwards, right? And when we have dispersive systems, right? I already mentioned about dispersion to you. Sometimes this is also called a wave packet, because there's a packet of waves that usually starts in one way and eventually develops into something like this, okay? Well, and there are equations, for example, to study the dynamics of the envelope, right? Instead of the whole thing. And actually, interesting enough, I mentioned this very quickly when I think I did at least, I don't know, or either both the fluids course or the PDs course. Some of you have taken with me either one or the other. And there are equations for the envelope, which is Schrödinger equation, which comes from quantum mechanics, but appears without the same interpretation of probabilistic interpretation. It's just the equation for the amplitude. Well, in Fourier space, this is nothing more than this. The carrier you want to shift the spectrum, you multiply by this rotation in physical space, right? But it has physical interpretations. Another one, dilation, which is this. Okay, if you rescale x, this is what you do to the Fourier spectrum. So I like to think of this, just because my brain works better, is that if I do this, instead of c, I put an epsilon. Right? What I'm doing is ridiculous, right? I'm just substituting c for 1 over epsilon. But it's basically because, in particular, some of you who had done other courses with me, it becomes a little nicer to talk. So if I have a function, and suddenly I rescale it on a fast variable, right? So epsilon is small. So if epsilon is small, like epsilon is 10 to the minus 3, that means when x, so this is 10 to the minus 3, so this is like 1,000x. So when x varies from 0 to 1, the function varied from 0 to 1,000. That's why it's a fast variable. So this is sometimes used, this kind of rescaling we use when you have rapid variations or fluctuations or whatever, right? So if you change variables and you rescale it like this, right, you go from the reference variable to a fast variable. In Fourier space, what you're doing is you have a slow variable, and you're rescaling the amplitude by epsilon. And this is nice. This is intuitive, because remember I mentioned to you, let's think of a Gaussian, which is a great object to play numerically. Why? Because it looks like a wave, a smooth wave. In many cases, it is a wave, right? Does not have, in most cases for us, a probabilistic interpretation. The Gaussian is just a smooth C infinity wave, very useful, right? And the other good thing is that the Gaussian, in my mind, I already know the Gaussian in physical space is a Gaussian in Fourier space, right? But here we see that if the Gaussian is fast, which means it's skinny in physical space, it is broad in Fourier space. Excuse me, why? Because something that varies rapidly in physical space needs a lot of frequencies in Fourier space to represent it, needs high frequencies to represent it. In other words, something which is fast in physical space is of broad Fourier content in Fourier space. So here it is. And the amplitudes gets rescaled like that, okay? So this is a good thing. If you're playing with a wave, right, and you're looking for instability, for example, right? I mean, if you already did some tests for like that wave front or this or that, or seeing dispersion, right, with Lux Friedrichs, Lux Wendorf, and so on. If you make your wave skinnier in physical space, you're invoking more Fourier modes, right, in Fourier space, and it goes like this. Okay, so this is a good property to know. Okay, then the other ones I'm not going to write, okay? It's here in the notes like conjugation. So if you conjugate you end up conjugating Fourier space with a minus sign. This is like just playing with the formulas, right? And differentiation I already mentioned. And there's a few other ones. And then also there's, that I think Trefethen calls like theorems, but it's things like several properties to check. Let me read just a few so you see it's like things easy to check. Like if u of x is an even function in physical space, then it's even in Fourier space. If it's odd, then it's odd. If it's real imaginary or real or imaginary, things like that. Okay, so those are simple things to check. I'm not going to write this. So what I want to do, good, so I have the last half an hour, is to prepare ourselves. So for those who have done other courses with me, it will refresh your memory regarding the instability of interfaces. Some of you have not done these courses with me. I'll give you a little bit of the motivation of where this comes from, but then we're going to get into something which is new for everybody. It's how to deal with these strange and interesting mathematical objects numerically. And we're going to see a problem that has a legitimate instability, so it has a dynamical instability, but if we're not careful, it's also going to have a numerical instability. So if you're studying this problem, you got to make sure you're taking care of the dynamical instability. Don't get confused with the numerical instability, right? It's that famous thing I mentioned to you about the numerics of dynamics and dynamics of numerics. And in this topic, there were some papers published by good people in the 80s, whatever, that they were actually talking about the dynamics of the numerics, saying it was the numerics of the dynamics, right? So, and this is good because this forces me to mention two things that I'm sure many of you have not seen it before and have seen maybe with me. I know some of you have, but have none of you seen it numerically, okay? And that's the challenge. Okay, so let me start presenting the problem so that next class we can start addressing it numerically and in particular checking things of the numerical stability and numerical properties and so on. So we're going to see a problem which is called the Kelvin-Helmholtz instability of an interface. And what is nice too, because I'm going to show you a problem that was a research problem that called the attention of many people, applied mathematicians, in the 90s. So for you, this is a long time ago. For me, it's not, because you're young. But scientifically, it's not a long time ago, right? A few decades ago, this problem was a scientific computing problem because proving things was very difficult. And there were a few papers, which I'll mention to you, some aspects which were really important, called the attention of the community. So this is the problem. So this problem of interface instability is the following. So let me see how I give it to you. So let me put it like this, look. So this is an interface, okay, separating a flow and another flow where there's like a liquid, right, fluid going this direction and the fluid going that direction, and this is called a, this is called a shear flow, okay? Shear flow is, in Portuguese, would be called, let me say in Portuguese, escoamento cisalhante, where cisalhante and shear, to some extent, means like a little bit like cutting something, right? Why? Look, if I want to cut this sheet of paper, right, I saw this in the fluids course B, I hold one hand fixed and I pull the other one down. So there's a relative displacement between my hands, right? So I could also, it's difficult to do this, but I could also cut a piece of paper, making this hand go to the right and this one going to the left. Usually we stop one. So there's a relative motion. So this is a shear flow because of this, okay? And this problem, which was initially associated, I mean, a motivation for it could be, and this is another example I give. I mean, I'm not the one who invented this, right? So if you have an airplane and you take a slice of the wing, it looks like this, okay? And as the airplane flies, you have this, okay? And the wing is designed by Bernoulli law, whatever, to have a lift, so the speed above is much faster than the speed below. Okay? And when you get to this side, when you get to the tip of the wing, basically here, you have more speed than here. And that's what generates lift. Bernoulli law, blah, blah, blah. Those who did fluids know what I'm talking about. Those who did know fluids, just think of this as a fun, cultural, scientific talk. Don't worry about it. You don't need that for the course. Okay, so therefore, you have this shear flow. Well, if you put yourself in a reference frame, this could be equivalent to this by taking the average, okay? And if you're going either way, you can go this way, okay? No problem. So this is the shear flow. And people realize actually behind the wing of an airplane, usually there's high turbulence here. This goes like this, starts oscillating. And there's a mechanism related to that, and this is what's called the Kelvin-Helmholtz instability. If you think of this, the orange being the interface, okay, separating fluid above and fluid below the wing. Okay, so then the more mathematical problem that Kelvin and Helmholtz studied is that, okay, this is a complicated problem to understand, blah, 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 blah. So let's try to make it as simple as we can, which, as you will see, is very complicated. So let's say, okay, this is a crazy form of the oscillation. Let's think of that the oscillation is periodic, that the perturbation is periodic. And let's take the simplest periodic perturbation, like sine of x. So the problem starts like this. You pick a window here, which is, let's think of this as the window. And let's say, oh, let me study mathematically what happens if I have a small periodic perturbation of size epsilon, and where the perturbation is just sine of x. I don't understand this problem, so let me do the most simple case I can. Okay? And people you can solve, this is a 2D problem, right? 2D problem. You have a domain above and below, so people could call this domain omega 1 and omega 2, divided by the curve orange, and the flow is incompressible, blah, blah, blah. So part of the story is that the simplification, as you can think of the flow satisfying Laplace's equation on the top, Laplace's equation on the bottom. Basically, you can rewrite this problem as in complex variables, saying, oh, I have an analytic function, which is harmonic parts up here, harmonic parts down there, but it has a weird behavior over this curve. Actually, it has a jump and ta-da. And then people came up with the equations I'm going to show to you, which in fluids and PDs, people have a better idea where it comes from. Here, just accept it as an equation, and I'll give you a little bit of the intuition where needed, hopefully to help. But it's an integral differential equation with weird things that one can solve numerically. And since this is a numerical course in differential equations, I think this equation has lots of nice aspects for us to address, right? So that's why I decided to show it to you. Okay, so therefore, let's skip some pages here. There's some references. Doesn't matter. I think I can put this here. So the problem can be written as an integral differential system as follows. Look at this. Looks, at first, for those of you who have never seen this, it looks very complicated, but my job is to demystify it and show you interesting aspects, in my opinion, very interesting aspect from computational mathematics. Okay, and that's new for everybody, the computational mathematics associated to this. So let me first write the equation we have to solve. And at first you're going to see, wow, this is scary, complicated. Okay, so let me explain the problem to you. And the problem is, at first, scary. But my idea is to, in particular, show to you that we can actually do it. Maybe I'll give it to you. The linear problem, we can, I mean, the nonlinear problem is, after you understand the linear problem, is not that much more difficult. It is more difficult. But we can understand how to solve this on the computer, the linear problem, which at first looks scary, but after a few classes, it will be not scary at all. Okay? So look at this problem. So what is Z? Z is X of ST plus I S of ST, because this is X, this is Y. Okay? So using tricks, I mean, we learned this, a little bit of this in the PDEs course, in the fluids course, is that we can use complex variables to solve this problem. And at the end, we rewrite this problem in the real and imaginary parts of this equation, so we don't even have to use computationally complex variables, but the original formulation uses. So what does this say? At least for us, and imagining that nobody here did fluids with me, nobody here did PDEs, the theory with me, and applications, okay? Because this is a numerical course, and there's no prerequisite. So I'm going to do, the model is, the first thing which is beautiful, a 2D problem is reduced to mathematically to a 1D problem. Look, it's a 1D problem. I'm only solving this in terms of the orange curve, where this is S equal to 0, and this is S equal to 2 pi. And eventually, we will discretize this. Okay? In the PDEs course, I teach you that if I know everything about this curve and so on, I know everything inside the fluid, right? Because of the harmonic properties of the function, but you don't have to know that. Just know this as an information, why this is a cool formulation, right? I can reduce the problem to 1D, and if I know everything about this curve and the related potential, I know everything inside, right? Looks like magic, but it's not. It's mathematics. Now, when we reduce the dynamics to the orange curve, I get that the evolution of the curve, see, this is the interface. Interface, maybe I should write it like this to be more parametrized by S, right? S from 0 to 2 pi. It's periodic. So this is the position of the interface in the complex plane. It's time, it varies in time according to this crazy equation which I have to explain to you. This is a singular integral. I'll tell you in just a second before we finish the class, because I wanted this to be in your minds until Monday. So this is a singular integral I have to explain to you. Now, this is somehow what we call the strength of the interface in the sense of the strength of the singularities, right? Those of you who did fluids with me knows that it has somehow to do with vorticity, blah, blah, blah. I will not even get to this or else the class becomes large. Just think of this. This is a coefficient which means the strength of the singularity. Which singularity? Of this cotangent, because when S is equal to S prime, boom, this guy blows up like 1 over S, like 1 over X, okay? So when S, look that S and S prime are on the interface. So see, this is S, and I'm integrating over S prime, okay? So when I'm integrating and I go over that point, poof, it explodes like a pole, like 1 over X. So that's why I can think of this. So mathematically, those who don't know fluids saying, I have an integral, which is a singular integral. I'll explain to you in a second. I want to do this before I leave. Okay? Where this is the sort of intensity of the singularity, right? Wherever S is, and whenever this guy hits the singularity, it blows up. Okay? I have to learn how to deal with this integral. And I can deal with it with high precision in a beautiful way. Trapezoidal rule. This is so amazing, right? If you do the trapezoidal rule in the right way, you evaluate this singular integral that does not make sense in the Riemann sense with great accuracy. And eventually you're going to test this so you believe it, okay? Now, this tells me how the strength changes in time, because as the interface is changing, the strength of the singularity changes in time. It has a physical intuition to it. I'm not going to explain it to you. Let's just think mathematically, okay? So the intensity, which is the derivative of this guy, is the intensity, varies in time according to these two physical parameters, surface tension and density of the fluids, right? You know what a density is. Maybe you don't know what a surface tension is. A little bit like, it acts a little bit like an elastic membrane, but don't worry about it, just two parameters. And this guy evolves according to the curvature. So this is the curvature in the parametrization. So the more the curvature, the more this guy changes. So if the interface is flat, this guy is constant. So since I'm going to start with a small perturbation about a flat interface, this is my initial condition. Z, the position of the interface, is x plus IY, where x is the same thing as S, and y is a small perturbation, sinusoidal perturbation in the vertical direction. And the initial strength is constant. Everybody's the same. I'll let it evolve according to the curvature. Okay? Looks like a scary problem because it's more than an integral differential system. It's a singular integral differential system. Okay? Now, as you will see, I'll give you tricks where we can discretize this part, and it's going to look like a system of ODEs. But first, I have to know how to deal with this guy. And we're going to deal with this in the linear case. Okay? I'm not going to do the full non-linear case. Let me just do at least the linear case, where in the linear case, the curvature is going to end up being just YXS, SS, okay? And so we'll see this in the future, okay, without doing all the details. But now let me just mention at the end of the class what is a singular integral for some of you who haven't seen this. And it's here in the notes. The example is the 1 over x. So and you know, and what's nice is that it's an integral that does not make sense in the Riemann sense, but it's a great modeling object. It's a useful thing. It's not a crazy thing. Okay, so this singular integral can be motivated by this integral here. Right? Many of you have seen this with me. So this integral does not make sense This integral does not make sense in the Riemann sense, right? This integral does not make sense. But there is what's called the Cauchy principal value, where the notation is like this, sometimes principal value. Or I prefer this notation because it's simpler to write, just minus a. Okay? In which the idea, right, by Cauchy, is to take the limit, opens a window here, right, and takes the limit as this window closes. So the Cauchy principal value, the definition is the limit as epsilon goes to 0 of the integral from minus a to minus epsilon plus epsilon to a dx. Okay? And in this case, it's equal to 0. But this is the definition in general. Okay? So in this case, it's 0. So basically it's like this. You're trying to see if this minus infinity and plus infinity cancel each other, right? We know we cannot sum minus infinity to plus infinity. It's not a number, right? It's a limit. But the idea is that you want to see the rate at which these two guys are blowing up. And this exactly captures that actually for any epsilon, it's 0. So in the limit, this sequence converges to 0. It does not have to be 0, right? Right? Okay, particularly if you have an f inside here, right? Or for this guy here, it does not have to be 0. But it's the Cauchy principal value of this integral, which means you open an epsilon window about S, right? And you compare. And this is physical. This gives us actually for I'm going to mention also the Plemeli formula, so on, and things that you guys have been studying, which is it gives you values above, the right velocity above, below. It's a beautiful thing, right? Related to analytic functions, which are actually more appropriate saying sectionally analytic functions. Analytic on the top, analytic on the bottom, but it jumps, okay? I'm not going to do much more than this. And actually, if you see, I think, Márcio's seminar, in the seminar course, he will be explaining these things in more detail. Right, Márcio? Yeah? Okay. So, but the nice thing, which he won't mention, and none of you have seen, is how do we compute these guys on the computer, this crazy integral on the computer, to make sense of it. And it's very simple and very beautiful. So that's part of the story that I want to tell you. So what I'm going to be doing next class is, okay, let's not solve this guy. Let's solve its linear version, right? I'm going to show you, indicate how you get the linear version, blah, blah, blah. And we'll learn how to solve the linear part of it, because then we'll learn a few of these techniques I am mentioning, okay? So this is a good place to stop. And on Monday, we come back to this crazy equation, which will not become crazy soon. You'll feel very comfortable with it.